This video is an introduction to antidifferentiation. Before we start to talk about antidifferentiation, let's make sure we understand what it is. It really is, you're given a function, you kind of want to work backwards from it to find what function was the original function before you took the derivative. So we're going to find the antiderivative. So if I give you the derivative of a function, you should be able to work the opposite way to find the antiderivative now. So just for a small example, I say if g prime of x equals 4, what was the original function g of x, right? I'm asking this kind of, informally now. Later on we'll talk about some notation things. You might be able to tell, right? So if you got the derivative of something and it came out to a constant, usually it would just be the function times a variable, right? So g of x is actually equal to 4x is probably your response, right? Because the derivative of 4x gives you 4, right? That's what you're really asking yourself. What did I take the derivative of to get to 4? Well, I would take the derivative of 4x. But how do you know it's just 4x? In other words, how do you know it wasn't g of x equals 4x plus 5? Because, right, even if you were to take the derivative of 4x plus 5, the derivative of 4x would still give you 4. The derivative of 5 would go to 0, though. So there's this constant here, and the derivative of a constant always goes to 0. So you really don't know what the constant would be here, right? It could have been g of x equals 4x minus 1,000, because the derivative of that is also, right, derivative of 4x is just 4, derivative of 1,000 goes to 0. So you take these constants into account. So the general form, all right, so the general form would be this function g of x equals 4x. We have 4x in all of them. And then what we do is we write plus c. And the plus c means, plus a constant. We just don't know what the unknown constant would be. Right? So that's what that really is showing us. So g of x equal to 4x plus c. In general, I'll write this out and then we'll kind of do some more examples. So in general, if we have two functions with the same derivative, then I'll say capital F of x. Okay, so in general, if we have two functions with the same derivative, then we say capital F of x equals capital G of x plus c, where c is a constant. Now, when I say that, what I really mean is that f of x and g of x are going to be, the same exact function. They differ by a constant, kind of like, these two functions we had up here. And then just for information, right, when we find the original function from the derivative, it is called the antiderivative. So when I say we're trying to find the antiderivative, you're trying to find the original function from the derivative. All right, so all this is saying is that the functions differ by a constant like we had above. when we try to find the original function given a derivative, we're finding the antiderivative, and that's what we call antidifferentiation when we're doing this. So we'll do an example down here. So in this example, if I said find the antiderivative for y prime equals x to the third power. Well, let's think about it. First off, the original function is going to be called y, because the derivative was y prime, so the antiderivative should be called y. And it's equal to, well, how do you get x to the third power? Well, when you take the derivative, right, and you have a variable to a power, usually that power was decreased by 1, right, to get to here. So to get the derivative, I would have taken 1 away to get to x to the third. So I know that the original function would have been something with an x to the fourth, right, because I would have to increase it by 1 if I'm going the opposite direction. But remember what you normally would do. You normally would bring the power down in front. If I brought this down in front, I'd end up with 4x to the third, and I need it just to be x to the third. So what I really do is I divide by that same new power. In other words, right, I added 1 to the exponent, but I divide by whatever that same new exponent would be. And the reason I do that is because when I go to take the derivative of this, I would bring this down in front, and then it'll cancel out, which is what I needed to do. So really what you do is you add 1 to the exponent, right, to go back to the original, but then you have to divide by that same new exponent. And then don't forget plus c, because there could be a constant here that we don't know, right? Because as long as it's a constant, we take the derivative of a constant, it goes to 0. So y equals x to the fourth over 4 plus c would be the antiderivative of y prime equals x to the third power. And we can be more general with it, right? So if I wanted to talk about this generally, right, so if I said generally, and we'll write this more formally in a little bit, but if I have y prime equals x to the n power, and a key thing here is that n doesn't equal -1. That's a special case we'll talk about in a minute. But generally, when y prime equals x to the n power, when n doesn't equal -1, what you do to get y, the original function, right, you would get y equals, well, what did we just say? We said that you added 1 to the exponent, right, so this would be x to the n plus 1 power, and then you divided by that same new exponent. Well, this exponent is called n plus 1 generally, so divided by that same new exponent, n plus 1, and then we have plus c at the end because, you know, we have a constant. So this is just in general. The way we write the antiderivative, all right, maybe I'll write that on the next page. So the way we write the antiderivative. Right, the way we write the antiderivative, in other words, to give you instructions on taking the antiderivative without writing out, take the antiderivative every time, is, and it's this kind of elongated S looking thing, right? So that means take the antiderivative, all right? So this is giving you instructions saying take the antiderivative. And then you'll see a function here. So I'll put, you know, x to the third, just to go along with the last example. So take the antiderivative of x to the third, and then we write dx here. It'll always be with respect to a variable. So this dx means with respect to x in this case. If it was dy, it'd be with respect to y. If it was dz, it'd be with respect to z. You need this, though. It's giving you instructions. It's kind of like when you were taking the derivatives and we had d over dx. So it's saying take the derivative of the function with respect to x. So this is taking the antiderivative of the function with respect to x. And then, you know, if I was to evaluate this, right, so this is a way of me asking you the same question we just did. What's the antiderivative of x to the third dx, right, with respect to x? Well, you add 1 to the power, we said, so that'd be x to the fourth power, right, because you're working backwards now. then you divide by that same new power. So you divide by 4, and then plus c, because there always could be a constant at the end. But this is the general way you would write the antiderivative. So in general, if I write the antiderivative of some function I'm going to call f of x here, dx, all right, so take the antiderivative of f of x with respect to x, it's equal to, just to call it something, the antiderivative of f of x I'll call capital F of x, all right, plus c. All right, so that's just kind of how they generally show it. They're saying when you take the antiderivative of a function f of x with respect to x, you get the antiderivative, which we're labeling capital F of x, plus c. This is also called finding the indefinite integral. So if you hear the words integral or integrate, right, that means take the antiderivative. The process is called integration. So when we're talking about finding the antiderivative, you might hear antidifferentiation. You might also hear integration or integrate. The indefinite integral means that it doesn't have any limits of integration. There's no numbers involved to substitute in. The definite integral we'll talk about a little bit later, which will have values that you would need to substitute in. So, I mean, that's just kind of a general overview. Now we'll go through the basic integration rules. So this next part is kind of important to memorize, but you really memorize it by doing it as practice more than anything else. So basic integration rules. So I'm going to write the rules out and I'll show you examples of each as we do them. But again, the practice is what's really going to make sure you understand the rules. So the first rule says if I have the integral of k with respect to x, where k is a constant, and then the antiderivative of this would be equal to, well, how would you get k? Well, if k is a constant, it's kind of like that first example we saw. It's k times x and then plus c, because if you have the antiderivative of a constant, it had to have come from a constant times the variable to get there. Let's take a look at some examples just quickly next to this. So that's the first rule. For example, if I said take the antiderivative of 6 with respect to x. Well, what function gave me a derivative that was 6, right? That's how I find the antiderivative. Well, the antiderivative, according to this rule, says this should be 6 times x. Now, when we say with respect to x, remember, this stuff is just notation. It's going to go away. The antiderivative of 6 is 6x because they said with respect to x, well, you know the variable's x. And then don't forget plus c because there could be an unknown constant here. You could check this. The derivative of 6x, right? The derivative of 6x is just going to be 6. That's what it shows you. Derivative of c goes to 0 because it's just a constant. If I said the antiderivative of negative 15 with respect to x, well, what's that going to be? Well, it's the antiderivative of a constant, right? So it's going to be negative 15 and then x plus c. Because the derivative of negative 15x gives you negative 15, right? And then there always could be a constant here because the derivative of the constant will give you 0, so we don't know what the constant is, so we put plus c. And let's look at one more for this one. If I said the antiderivative, all right, of 9 dt, this is saying take the antiderivative, right? Take the integral of 9 with respect to t. So t is my variable now. That's what that's telling me. So what's the antiderivative of 9 with respect to t? Well, it would be 9t plus c. And that's because the derivative of 9t gives you 9. So if you have just the antiderivative of a constant, right, it's always just the constant times whatever variable we're taking it with respect to, plus c, plus the unknown constant. let's take a look at some other rules. If I said I had, and we just kind of talked about this a minute ago. So that first rule, right, this first rule here that we just talked about was very similar to what I asked you about finding the antiderivative of 4, right? And that's what we did. We ended up with 4x. We had all these different possibilities, and we wrote it as a general 4x plus c. Here, it's just, I'm writing it in the notation with the antiderivative in it. So the second rule says if I take the integral of x to the n power dx, we want to find the antiderivative of this. All right, remember we just talked about it. As long as n doesn't equal -1, and we'll talk about that special case in a minute, we know that from what we just said, we add 1 to this power, right? So how do you get to a power here? For when you got the derivative, you subtracted 1. So to work backwards, you have to add 1. So this would be x to the n plus 1 power. And then, remember, you want to divide by that same new power, n plus 1. Because remember, you bring it down, that's going to cause it to cancel to get to the x to the n. And then we put plus c at the end. And remember, this is for n not equal to -1. If n equaled -1, keep in mind what would happen. -1 plus 1 would make this a 0 denominator be undefined. So it's a different rule for when n equals -1. But for all other cases, x to a power, you add 1 to the exponent and divide by that same new exponent, and then plus c at the end. So let's take a look at a few examples here. If I said I had the antiderivative of x to the 5th dx, and make sure you have that dx in there. Don't skip over that. You need that because it's telling you the variable with respect to. Well, what's the antiderivative here? Well, it's x to a power, right, other than -1. You add 1 to the exponent, so it's x to the 6th power, divide by that same new exponent, divide by 6. And that's really how I think about it. I always say just divide by that same new exponent. And then plus c. So I don't really memorize the formula. I just say add 1 to the power and then divide by that same new power. And then make sure you have plus c at the very end of it. So x to the 6th over 6 plus c is the antiderivative of x to the 5th. And you might see people write this as, you know, this is the same as saying 1/6 x to the 6th plus c. They're equivalent. It's up to you how you want to write it. More often than not, I kind of write it like this just because it's easier to think about the division. But having the fraction in front as a coefficient is fine. Just make sure the variable is right next to it, or in the numerator. It can't be in the denominator. Right, so either of these is okay for your answer there. Let's take a look at a couple more. If I had, label these a and b so it's easier to work with. If I said I had the integral of 1 over x to the 4th dx. Just like when you take derivatives, if you have this x in the denominator and it's a power other than 1, you want to rewrite this. And to rewrite this first, right, RW stands for rewrite here. I'm just rewriting it in an equivalent form. I'm not taking the antiderivative yet, so you still want the integral there. You still want the antiderivative of, how do I rewrite 1 over x to the 4th so I can use the power rule? Well, it's x to the -4, right? It's moving the variable up to the numerator, so you make the exponent negative. And then with respect to x, so I'm just rewriting that middle part, right, the 1 over x to the 4th, just like I normally would when I'm taking derivatives. And now I'm ready to take the antiderivative. When you take the antiderivative, that's where you drop the symbol and you drop the dx, because those are notation. So the antiderivative of x to the -4, what do? Well, you have to add 1 to the exponent. So it's x to the, and be very careful here, -4 plus 1 makes this -3. And then you divide by that same new exponent. So you're dividing by -3, and then we have plus c. Don't write the integral symbol again. Don't write the dx again, right? You've done it. That's the operation. Once you're here, we want to simplify this. And to simplify this, I don't want negative exponents in my numerator. So remember what a negative exponent tells you to do. It tells you to move it to the denominator. A negative in front of the 3 is just the sign of the number. So what's left in the numerator? Well, just 1. Don't lose that. You need the 1. Over -3x to the power now, when you move it down, the denominator becomes positive. So 1 over -3x to the 3rd plus c. And more typically, you will see that negative sign. Remember, for a fraction, it can be in the numerator, denominator, or right out in front. More typically, you'll see it out in front. So -1 over 3x to the 3rd plus c. These are equivalent. I would accept either of these. But you do want to rewrite it without any negative exponents appearing in your answer. How about if we looked at this one here? If I said I had the integral, right, or the antiderivative of the square root of x to the 5th dx. Well, first thing, if you have roots in here, is just like when you're taking derivatives, you want to rewrite this. So you want to rewrite this as x to a power. So as a rational exponent, this will be the integral of x to, what's the power on this? Well, it's 5 over whatever the index of the root is. In this case, the index is 2, so it's x to the 5 halves dx. Remember, this is a rewrite step, so I still need the integration notation here. I'm not actually doing the operation yet. Once you've done that, we're playing the same game as we had before. We have x to a power that's not -1, so we have an x to a power. What do? Well, you add 1 to the power, so x to the, what's 5 halves plus 1? Well, that's going to be 5 halves plus 2 halves, so it's 7 halves. And then we said divide by that same new power. Now I write this down here so you can see it. So you're dividing by that same new power, just like the rule has told us the entire time, right? Add 1 to the power, divide by that same new power, and then put plus. See? But we don't want to leave this as a complex fraction. When you have a fraction divided by a fraction, remember what you do. You multiply by the reciprocal. So we multiply this by 2/7 x to the 7 halves plus c. And you can leave it like that. I don't care if you rewrite this as a radical or not. But I do want to make sure that you understand how to rewrite it if you needed to. But you can leave it in this form and you have the derivative. But do not leave this with the 7 halves down here unless I ask you not to simplify your answer. The important thing to recognize here is that if you took the derivative of this, right, you should be getting what was inside of the antiderivative, right? If I brought 7 halves down in front, taking the derivative, 7 halves times 2/7, that cancels to a 1. Then we'd have x to the, subtract 1 from the 7 halves power makes it 5 halves power. And then the derivative of c, which is a constant, derivative of a constant is always 0. So you do get the x to the 5 halves. And that's how this, why this actually works. All right, so if you have x to a power other than -1, add 1 to the exponent, divide by that same new exponent, and then add the constant to the end. The next rule, we'll talk about what happens when x does equal -1. So this is a special case. This will be rule 3. And this is the integral of 1 over x dx. And really all you have to ask yourself here is, how do I get 1 over x as a derivative? What function gave me a derivative that was 1 over x? Well, the function that gives you a derivative of 1 over x is the natural log of x. Right? Because the derivative of natural log was always 1 over whatever's on the inside, so 1 over x. And then make sure you put plus c at the end of this. More typically in calculus, you'll see this is the natural log of the absolute value of x. The textbook that we use doesn't show this, but really it is natural log of the absolute value of x plus c. The reason we write this is that the argument of log has to be positive value. So if we don't have the absolute value bars, then we could end up getting a domain error if we didn't have it there. So really, I prefer if you use this as the rule. But our textbook, you might see it without the absolute value bar, so I want to make sure that you understand why that's the case. Now remember, this special case here, this 1 over x, I didn't rewrite it because if you were to rewrite this, this is actually the integral of x to the -1 dx. That's the special case that was not included in this rule, right? The rule above said n doesn't equal -1. If you were to rewrite this and then try to use the power rule, you would have added 1 to the exponent, which would have made it 0, and then you would have divided by 0, which is undefined, so you're not allowed to do that. So this is the special case. You don't rewrite this. If you have 1 over x, you want that x to be in the denominator. So if x has a power of 1 in the denominator, you essentially want to keep it there. You don't want to rewrite it. Let's take a look at the next rule. The next rule is number 4. If I have the integral of some constant k times some function f of x with respect to x, that's the dx. Just like with derivatives, if there's a constant in front, you can just keep it in front and then proceed as normal to take the antiderivative. So you can keep k in front, and then take the antiderivative of the function f of x dx. You'll do this kind of naturally as you approach the problems, but let's just see a couple of examples to make sure we've got it. So if I said for these examples, I'll call this first one A. If I said you want to take the antiderivative of 5x to the 7th dx, what it's really saying is you have 5 in front of a function x to the 7th. You can keep 5 in front. And then how do you take the antiderivative of x to the 7th? Well, you would add 1 to the exponent, so it becomes x to the 8th. And what do? You divide by that same new exponent, so you divide by 8. And then we'll put plus c here. A lot of times you'll see people write this as just 5/8 times x to the 8th. You could also put the 5 in the numerator of the fraction. If you wanted to check this, take the derivative of it, right? Bring 8 down in front. 8 times 5 is 40 divided by 8 would give you 5, and then subtract 1 from the exponent gives you x to the 7th. The derivative of c goes to 0. But that's what it's saying. It's saying keep the constant in front and then take the antiderivative of the function piece. Remember, this is if you have a constant times a function, not just if you have just a constant. If I had the integral of 3 square root of x to the 7th with respect to x. Remember that dx is there because it's saying with respect to x. First thing I'm going to do, well, if I see that radical in there, I'm going to rewrite it. So I'll rewrite it, and this will be the integral of 3x to the power of 7 over the index of the root, which is 2 dx. And sometimes you might see it written before they take the antiderivative. They say, you know, keep the constant in front like I did up there. You might see it written as 3 and then the antiderivative of x to the 7 halves dx. That's the same thing as what we did over here. We just kept the 5 in front as we did the operation. But this is really what the rule says. But it's an unnecessary step to write most of the time. So now we're ready to take the antiderivative. Remember, that's when you can eliminate the symbols that talk about it. So we would have 3 times, what's the antiderivative of x to the 7 halves? Well, it's x to the 7 halves plus 1, which would be 7 halves plus 2 halves, which is x to the 9 halves, divided by 9 halves, and then plus c. And then we're going to rewrite this. Remember, when you divide by a fraction, you multiply by the reciprocal. So it's really like 3 times 2/9 x to the 9 halves plus c. And then making sure that you do reduce this. The 3 and the 9 cancel out, right? This would be canceled to a 1 over 3. So I end up with 2/3 x to the 9 halves plus c. So make sure you do reduce this. If you multiplied this, you would have gotten 6/9. Make sure you do reduce it down to 2/3. The next example, or the next rule, I should say. I'll call this rule number 5. It says if you have the integral of e to the ax power dx. This is a very specific rule. It's for e to a constant times x in the exponent. The rule itself, you know, defining it generally, is e to the ax over a plus c. So it's not like the power rule where you know add 1 and divide by that same new thing. It's really like, you know, when we took derivatives of e, you would write exactly what you see and then use the chain rule to take the derivative of the exponent, right? So here when you do the antiderivative, you're actually saying to yourself, okay, derivatives of e, I wrote exactly what I see, so antiderivatives, I should have exactly what I see. But then use the chain rule on this. When you took the derivative, you would have just gotten a. So if I was getting a times that, how do I get rid of it? Well, I have to divide by it. So it's kind of using the opposite operation. I'm going to show you through an example. I think it's a little easier to see, and then we'll go through and do some other examples. So if I said I had, you know, the integral of e to the 7x dx. According to the rule I just gave you, right? This should be, the antiderivative of this would be exactly what you see, e to the 7x, and you want to divide by whatever was in front of x here, so you're dividing by 7. That's what that really shows. Right, and then plus c. This is a special case for e to the ax. If this was any other function up here, it doesn't work exactly like this. And then that would be the answer, right? E to the 7x over 7 plus c. I want to show you the check on it. The check would be to take the derivative of this, right? So the check here would say, you know, suppose I took the derivative, right, with respect to x of e to the 7x over 7 plus c. Well, what happens when you take that derivative? Derivatives of e, write exactly what you see. This over 7 is like a 1/7 constant in front, doesn't change anything. So the derivative of e to the 7x over 7, you'd write exactly what you see, e to the 7x over 7 times the derivative of the exponent, right, because it's a chain rule on e, so you'd multiply this by a derivative of 7x is just times 7. And then the derivative of the plus c would just go to 0, right, so this would be plus 0 just so you see it. And then what happens? Well, these 7's cancel out and you're left with e to the 7x, which is really what our argument was, and that's how you know that this actually worked. I wouldn't check this every time, I'm just showing you why it works. So it's because of the chain rule that we divide by whatever was in front of x when we do this, but it's very specific to integrals of e to the ax power. Let's look at a few more just to make sure we got that part down. So if I was to look at this example here, and I said, I'll call this one A. If I said I had the integral of negative 4 e to the 5x dx, this kind of combines rules, right? We have a constant in front of the function of negative 4, and we know that negative 4 can just stay negative 4 in front. The antiderivative of e to the 5x, remember how it works. It's e to the power of 5x divided by whatever was in front of x. So divided by 5 and then plus c. And then typically, you know, you'll see this written as the fraction negative 4/5 e to the 5x plus c, or you can put the negative 4 in the numerator. Either way is okay, but have an understanding of where we're getting this from. So the constant stayed in front. The antiderivative of e to a constant times x is just antiderivative of e, you wrote exactly what you saw, and then divided by whatever is in front of the x. Now we'll look at one more like this. If I had the antiderivative of 2e to the negative 3x dx, taking the antiderivative here, 2 in front, stays in front. Antiderivative of e to the negative 3x, it's e to a constant times x power, so you write exactly what you see, e to the negative 3x, and then you divide by that same, that coefficient of x, which would be divided by negative 3, and then plus c, right? Make sure you don't divide by negative 3x, right? It's not divide by exactly what you see. It's not like our other rule, right? You're just dividing by the coefficient. And then simplifying this, you could write this as negative 2/3. 2 over negative 3 is the same as negative 2/3. E to the negative 3x plus c. And then sometimes if you have a negative exponent, remember you might want that in the denominator. It doesn't matter so much when you have an exponential because we know that this can't become 0. So you don't necessarily have to rewrite that, but if you did, it'd be negative 2 over 3 e to the 3x plus c. So either of these would be okay. Let's do some examples where we got one more rule, and then we'll do some examples. This example here really just builds off of things we've already talked about, though. Really what this says is that if you have the integral of f of x plus or minus g of x, so you're taking the antiderivative, all right, dx, so with respect to x, of something that's being added or subtracted. What it really tells you that you can do, just like with derivatives, is that you can take antiderivatives term by term. So I could take the integral of f of x dx plus or minus the integral of g of x dx. In other words, you can do it term by term. As long as they're added or subtracted, these two functions, you can take the antiderivatives individually and just still add or subtract them. Now, if it's multiplication or division inside of here, that's a different rule. You can't just take antiderivatives of each piece. So let's do some examples with this. All right, and this pieces together kind of all the rules we've talked about. So for these examples, we're going to evaluate, and we'll do a few. All right, and they all have to do with the antiderivative. If I said for the first one, I had the antiderivative of 3e to the 6x plus the square root of x dx. Right? So it's telling me to take the antiderivative of that function. First off, I know I can do it term by term based on the rule we just talked about. Additionally, if I see the square root of x in here, I know I need to rewrite this. So your first step is a rewrite step. So I'm going to rewrite this as the integral of, now 3e to the 6x doesn't change. Remember, in this rewrite step, don't start taking integrals of some pieces and not others. Make sure you don't take any integrals until it's all rewritten properly. So 3e to the 6x doesn't need to be rewritten. You just keep it as it is. Plus the square root of x, so I wanted to rewrite that in an equivalent form. It'd be x to the 1/2 power with respect to x. And now I'm ready to take the antiderivative because I have the form I need. So how do you take the antiderivative? Well, the antiderivative of 3e to the 6x, remember 3 in front is a constant in front of a function, so 3 stays in front. Antiderivative of e to the 6x, it's e to a constant times x, so it stays that, and then you divide by whatever was in front of x. You divide by 6 plus the antiderivative of x to the 1/2 would be x to the, add 1 to the power, 1/2 plus 1 would be 3/2. And make sure you say it that way, don't say 1/2, keep it as an improper fraction. And then remember, you have to divide by that same new exponent, so I'm going to divide by 3/2. And then at the end of this, you want plus c. Make sure you put plus c. You're going to need that at the end of all these indefinite integrals. Make sure you put plus c there at the end. And then we will simplify this, as necessary. 3 over 6 does reduce to a 1/2, so I'll write this as 1/2 e to the 6x. Plus here, when you divide by a fraction, you multiply by the reciprocal. Don't leave it in this complex fraction form. So dividing by 3/2 is the same as multiplying by 2/3, so it's 2/3 x to the 3/2, and then plus c. Let's take a look at another one here. If I had, that was A, so this one I'll call B. If I had the integral of, say, 4x to the 9th minus 2 over x plus 1 over x to the 4th dx. So first thing when I look at this is I want to determine, do I need to rewrite anything to get it in the correct form? And you would here because of, you see this x in the denominator. So this is a rewrite step. RW is for rewrite. I'm not going to take the antiderivative yet. I'm just rewriting what I have in an equivalent form. So 4x to the 9th does not need to be changed. You keep it as 4x to the 9th. We have negative 2 over x. Now remember, this is x to the negative 1. That's our special case. You want to keep it as negative 2 over x. You don't want to change that form. Plus 1 over x to the 4th. That one you do want to write as x to a power. This is x to the negative 4. And then dx at the end with respect to x. So we're rewriting the last one because, we need the x to be to a power to use our rule. But here, because this would be x to the negative 1 power, remember our rule doesn't apply for negative 1. That's a special rule. So let's talk about what happens when you take the antiderivative. The integral of 4x to the 9th. Well, 4 stays in front. We have x to the power of, remember, you add 1 to the exponent, so x to the 10th, and you divide by that same new exponent, so you're dividing by 10. Minus here. Now this is 2 over x, but you can really think of this as being 2 times 1 over x, right? That's like a constant times a function. So the 2 will stay in front, so minus 2. And what's the antiderivative of 1 over x? Well, that's the natural log of absolute value of x. Keeping in mind that, right, when you see this 2 over x like this, 2's out in front, and then the 1 over x is what you're actually taking the antiderivative of, which is natural log of x. Do not write this as x to the negative 1, because then you get something that's undefined. You can't divide by 0. Plus here, the antiderivative of x to the negative 4. Well, negative 4 tells you you're going to add 1 to the exponent, so it'll be x to the negative. Remember, adding 1 makes that negative 3. And you divide by the same new exponent, so you're dividing by negative 3. And then you put plus c at the end always, because there's always could be an unknown constant. Now, if I don't ask you to simplify, you could leave it like that, but I assume you will simplify, unless I tell you not to. So 4 over 10, if this reduces, you should reduce it. And 4 over 10, they share a common factor of 2. So this reduces to 2/5 x to the 10 minus 2 natural log absolute value of x. Make sure you have those absolute value bars in there. They do matter. Here, this is a little interesting to rewrite. We have a positive divided by a negative. So I know this is going to become negative. So that takes care of the negative, and the positive sign gave you a negative. X to negative 3 moves it to the denominator. So in the numerator, I just have 1. This is going to be 3x to the positive 3. Remember, don't put this negative again, because we took care of it when we divided. Positive over negative made it negative. 3 stayed down there. X to the negative 3 moved down to the bottom. Has a positive exponent now. And then plus c at the end. And we'll leave it like that. And then maybe we'll look at one more like this. If I had the antiderivative of, we'll say, 4 over the 5th root of x plus 3/4 e to the 9x minus 7 over x with respect to x. First thing I should do is rewrite it. Remember, you're rewriting this in an equivalent form. We're not taking the antiderivative yet. We're just rewriting equivalencies to make it easier to take the antiderivative. So I have 4 over the 5th root of x. So 4 is a constant. We'll stay 4. The 5th root of x in the denominator would be x to the 1/5, but I got to move it up. So it's really x to the negative 1/5 plus 3/4 e to the 9x. That doesn't need to be rewritten in any other form, so I'll keep it as 3/4 e to the 9x minus here 7 over x. Do I rewrite that? Well, you really don't want to rewrite this as x to the negative 1, because remember, that's our special rule. Right, x to the negative 1, if you were to take the antiderivative of that, would give you something undefined if you use the power rule, so we can't do that. So we'll have minus 7. It's over x. You might want to write it as minus 7 times 1 over x, if that's easier for you to see. We're taking the antiderivative of all of this. And now we'll actually evaluate. This gives us antiderivative of the first part, 4x to the negative 1/5. Remember, you're adding 1 to the exponent. So negative 1/5 plus 1 is really the same as adding 5/5. So negative 1 plus 5 would give you 4 over 5. So x to the 4/5. And then remember what you do. You divide by the same new exponent. So I'm going to divide this by 4/5. And we'll simplify that in a minute. If you could do it at the same time, that's fine. I just want to make sure you see the rule. Plus 3/4 stays in front. E to a constant times x power, you write exactly the same thing, e to the 9x, and then you want to divide by whatever was in front of x. Don't divide by the x, it's whatever the constant was in front of x, so I'm dividing by 9. Right, so we have 3/4 times e to the 9x over 9, minus here we have 7, the antiderivative of 1 over x, the integral there, gives you, remember this is our special case, what gave you 1 over x when you took the derivative? Well, it was natural log, so natural log of the absolute value of, in this case, x, whatever the variable was, and then plus c at the end. And then let's simplify this. Simplifying this. Remember, when you divide by a fraction, you multiply by the reciprocal. So this is the same as saying 4 times the reciprocal. This is 5/4 x to the 4/5 power. Plus here, I have 3/4 times e to the 9x over 9. It might be easy enough to see that the 3 and the 9 share a common factor. 3, this is 1, this becomes 3, and you end up with e to the 9x over 12. because you're multiplying 4 times 3 together in the denominator. Remember, multiply straight through the top, straight through the bottom for fractions. Minus 7 ln x, or ln absolute value of x. Keep it like that. Make sure you have absolute value bars on that. Plus c. And then just simplifying here, these 4's cancel. I end up with 5x to the 4/5. You don't have to write this as a radical. Plus e to the 9x over 12. Or you could write that as 1/12 e to the 9x. That means the same thing. Minus 7 natural log absolute value of x plus c. So making sure you simplify these is important. You know, and then making sure you rewrite these at the beginning is also important. If you don't rewrite this at the very beginning, taking the integral, you probably won't get the correct answer. Let's just take a look at one more example here. So if I said to find, in this example, find f such that f prime of x equals 9x squared minus 4x minus 2, and f of 1 equals negative 7. So they're telling you the derivative of the function f, right, the 9x squared minus 4x minus 2, and they're also saying that f of 1, right, the original function, when the x value is 1, the y value should be negative 7. So what you want to do first is you want to find the general function, the one for just f of x, when you take the antiderivative of this. And then once you have that, we're going to use this initial condition they gave us to determine the particular solution. So if we're looking at this for our solution, the first thing I'm going to do is I'm going to say to find f of x, what I really need to do is I need to take the integral of f prime of x dx, right? That's really what it means, is that the antiderivative of f prime will give me the original function f. So we're looking at the antiderivative of f prime is what they told us, 9x squared minus 4x minus 2 with respect to x. And there's nothing to rewrite in here, so we're ready to take the antiderivative right away. So we get 9x squared, the antiderivative of that would be 9 stays in front, x squared, you would add 1 to the power, so that would be x to the 3rd power, and then you divide by that same new exponent, so we divide by 3. Minus, here we got 4x to the, remember this power is 1, so you add 1 to that would be 2, and divide by that same new power, so divide by 2. And then minus, if you have a constant, remember a constant here, take the antiderivative of that would be the constant times the variable, so minus 2x, and then we have plus c. So we can simplify this, and if you could simplify this as you're going along and you know what it's going to be, like sometimes people can see that the 3 would come out and you can do that, that's fine. I like to show it because I want to make sure you know what you did. So 9 divided by 3 gives me 3x to the 3rd, minus 4 divided by 2 gives me 2x squared minus 2x plus c. Now what I just found here, this was the general solution. I didn't actually answer the question yet, right? This is the general solution. If they just asked us to find f of x and they didn't tell us the initial condition, you know, this is our general solution for some constant c. What we're going to do is we're going to use this, all right, along with f of 1 equals negative 7 to find c. So now we're going to use f of 1 equals negative 7 to find what we call our particular solution, to find c and get the particular solution. So the x value is 1, the y value is negative 7. That's what that's really telling you. So f of 1 means you sub in 1 everywhere you see x, so it'd be 3 times 1 cubed minus 2 times 1 squared minus 2 times 1 plus c. And we know this should equal, right, f of 1 is equal to negative 7. So it really equals, right, when I do this, f of 1 is negative 7. So when I sub this into here, this whole thing should equal negative 7. And I'm solving this. Well, what's that give me? 1 cubed is 1, so it's just going to be 3 times 1 is 3, minus 1 squared is 1, so minus 2, minus 2 times 1 is minus 2, plus c equals negative 7. And what I'm trying to do is solve for c. make sure you understand that the x value gets subbed in. It's equal to the y value. So 3 minus 2 would give me 1. 1 minus 2 would give me a -1 plus c equals -7. And then we'll add 1 to each side. We end up with c equals -6. That's great. Now remember what you're doing with that. You're going to take c equals -6 and you're going to use it up here for our function f of x. So our particular solution, right? So f of x is equal to, well, we had 3x to the third. This all stays what it was. So 3x to the third minus 2x squared minus 2x plus, now c was -6, so I really could write this as just -6. And this is our function for f of x that is the antiderivative of this, right, and has this specific case, f of 1 equals -7. If they gave you a different initial condition, you would have found a different value for c here, which would have changed what the function was. But this here is what we call the particular solution. All right, so this is the particular solution. So a lot of times that when you find the antiderivative, you might know an initial condition, and then you can use that to give you the particular function rather than just the general solution for the function. So hopefully this video helped as a good introduction to antidifferentiation. We'll continue out throughout the rest of the chapter using this.